So last time, we started to calculate the partition function for our Ising model in 1D, both at zero field and at finite field. So at the end of the last lecture, we started to use a transfer matrix method for the Ising model at the finite field. So the partition function in that case is given by this trace of this exponential of the matrix, and we apply this periodic boundary condition for our convenience. Of course, we already showed that the different bounding conditions only lead to minor differences in free energy. In the thermodynamic limits, that difference doesn't matter. Okay, so we are free to use any bounding condition we like, and in this case, periodic bounding condition is very useful. So then we could simply just expand all the terms inside the trace of partition function, and when we do so, it is written in terms of the product of the summation over all the spins on different sides of the chain or the ring. Encircle the independent terms over nearest neighbor spins like this. Okay, so this is the product of all this matrix element for nearest neighbor spins. Say, for example, the first bracket is actually involving spin on side 1 and side 2. And the second bracket involves only spins for the side 2 and side 3 and so on and so forth. So we could separate the trace of this Boltzmann weight of all the spin on the chain or on the ring in terms of the product of summation over individual spin variables and of the nearest neighbor spins. But all this product, when we just multiply them together, we get back to this trace. So we are free to decompose the trace in terms of the product of this matrix. Each bracket is actually considered as some kind of a matrix, and which we'll define later. But if we simply just expand all the possible values of all these S spin variables, being plus or minus 1, then for each of the fixed spin variables of that, each of the bracket here is something like the matrix element of a matrix we call the transfer matrix, Ts1, S2, whereas Ts1, S2 is simply just the first bracket here. So in other words, we can simply just decompose this trace in terms of product of all this so-called transfer matrix. But we could formally define such a transfer matrix for the spin 1 and spin 2 in a 2x2 matrix form like this, where this S1 and S2 are the labels of those matrix elements of that 2x2 matrix. For example, when I write this T11 here, which means that both S1 and S2 take the value plus 1, and so on and so forth. So T1 minus 1 refers to that the first spin takes plus 1, but the second spin takes minus 1. And T minus 1 plus 1 is the reverse order, and T minus 1 minus 1 has the similar definition as T11. We have 4 possible values of the Ts1, S2, the transfer matrix, and they can be casted in the 2x2 matrix like this. So suppose we plug in this, say, plus 1 matrix element back to that exponential Boltzmann weight, and we get e to the h plus k, because this 1/2 h times 1 plus 1, which is h and S1, S2. Both being plus 1, so you get plus k here, and for this T1 minus 1, you get cancellation between S1 and S2 here in the Zeeman term, so you get 0 there, but you get minus k in the second term. And likewise, T minus 1 plus 1 takes this e to the minus k matrix element, and the minus 1 and minus 1 matrix element takes the value of the e to the minus h plus k. So in other words, when you sum over all possible value for all the spin variables on all the sides of this one-dimensional Ising channel ring, and effectively it is simply just sum over all possible spin values, and inside the summation you get the product of all this transfer matrix. So to see this matrix product or matrix multiplication property of that partition function. So we should remind ourselves the definition of the matrix multiplication. Suppose the matrix A is the product of this matrix B and C, and we could simply just write down the components of these matrices on both sides of the equation like this. And therefore, when we just take the sum over K and matrix B with element ik multiplied by the matrix C with the matrix Kj, and we sum over all this intermediate index, and this will be the matrix element for A for this element ij. And similarly, we could just remember the definition of the trace of any matrix as a sum over matrix element aii, where both indices are the same index, and we sum over just the one index I. In other words, we simply just, for example, the 2x2 matrix, we simply just sum over the diagonal matrix element. Then we get the trace of this matrix. Remember this definition of the matrix product and the trace of the matrix, and you immediately notice that this n is nothing but a trace of all this product of these matrices, T, which I call this T1, and T2, and T3, and so on, up to Tn. Where T1 refers to this Ts1, S2, and T2 refers to Ts2, S3, and so on and so forth. So you can immediately compare the summation over a bunch of these matrix elements multiply together. Okay, for example, this is simply just sum over the dummy variables S2 here, which represents this matrix product between this the first matrix, transfer matrix, and the second. So we keep multiplying the matrix together until we have this last one. This is Sm minus 1, Sn. Sum over all dummy variables as indices, intermediate indices there. So after we sum over all those intermediate dummy variables, effectively we take the matrix product. And you notice that the very first matrix element here, S1, is actually the same as the very last matrix element over there, S1. So effectively, this is the trace of all this matrix product. Suppose I denote this product, the matrix A, and this is nothing but the trace of matrix A, where A represents, the matrix product of all these transform matrices. But you'll see that in each of these brackets over here, in other words, the transform matrix, if you expand this 2x2 matrix of each of the bracket of there, you'll find that this is the same matrix. For example, T1 is actually the same as T2, is same as is same as Tn. As a 2x2 matrix, they all behave exactly the same. They have the same matrix elements because when you expand all possible spin variables for all of these brackets, each of the bracket there, so you find that the matrix elements are identical among all of these brackets. So all of these matrices are simply just the same matrix. So in other words, this trace of the big matrix A is nothing but the product of the same matrix. So remember, we need to sum over the S1 and Ts1, S1 to the power of n. So when we multiply all this transform matrix together, it's actually another 2x2 matrix with the indices or matrix element S1 and S1. So that's Ts1, S1. But effectively, we should add a nth power to this Ts1, S1 because this A matrix is nothing but the product of n transform matrices of the same type. So then what is this? Well, this is nothing but the trace of the matrix, transform matrix T to the power of n. So that's it. So now let's just summarize what we have. So by using the transform matrix method, we are able to simplify this partition function in terms of trace of the transform matrix to the power of n. So now the remaining job is to actually diagonalize a single T matrix or transform matrix. So we could diagonalize a single T matrix in a way that we are familiar with in this applied math. You know that we could perform a unitary transformation by this matrix S in such a way that this transformed matrix, which I call this T prime, is actually diagonalized. In this case, it carries two diagonal matrix elements, which I call this lambda 1, lambda 2, and they are eigenvalues. So lambda 1 and lambda 2 are eigenvalues. So we could very easily get this eigenvalue, but we will do that in just a moment. But let's just formally simplify this partition function even further. And suppose we can achieve that. We can certainly achieve this in just a moment. Suppose we achieve that. We know from the matrix theorem that the trace of a matrix T is the same as the trace of the unitary transformed matrix T prime, because S inverse S is actually unit matrix, and this is the same as what? It's inverse T and S, which is the same as trace of S as inverse and T, and this is unit matrix, and therefore the trace of the matrix T is the same as the trace of a unitary transformed matrix T prime. In other words, we only need sum over the diagonal matrix elements of a transformed diagonal matrix T prime, lambda 1 and lambda 2, and that's it. Okay, because the trace of T is the same as trace of T prime, and the trace of T prime is nothing but lambda 1 plus lambda 2. But what we want is actually trace of T to the power of n. In that case, this is the same as the trace of T prime to the power of n, and that is nothing but lambda 1 to the power of n plus lambda 2 to the power of n. So I use up all this blackboard space, and we will take a short break. When we come back, we'll continue finish up this transform matrix calculations. And we know that only one of them should be greater than the other. Suppose that we have the two eigenvalues, lambda 1 and lambda 2, in such a way that lambda 1 is greater than lambda 2, and later we're going to show that the property of this ground state and finite temperatures will be dominated by this largest eigenvalue. All right, okay, so let's take a short break. Just a moment ago, we arrived at this conclusion that the partition function for a one-dimensional ring of an Ising model takes this form, which is the sum over eigenvalues to the power of n, where n is the number of sites. And we assume that lambda 1, the first eigenvalue, is bigger than the value for lambda 2. So in other words, we could simply just rearrange this, the sum of these two eigenvalue to the power of n in such a way that this is lambda 1 to the power of n times this 1 plus something, where that something is actually the ratio of lambda 2 to lambda 1, and this ratio is actually less than 1. And overall, there is the power of that thing inside the bracket to the power of n. In the thermodynamic limit, n goes to infinity. So suppose I have a term like 1 plus, say, 0.4 to the power of n, where n goes to infinity, then we could simply neglect that 0.4 when n goes to infinity, because that term eventually will lead to just order of e to the minus alpha times n when n goes to infinity, where alpha is simply just the log of lambda 1 divided by lambda 2. And lambda 1 is bigger than lambda 2, so the log should be positive. And this is e to the minus alpha, which is positive value, times n, which is infinity. So this e to the minus infinity is actually negligible. So we could simply just forget about the second term in the thermodynamic limit. And therefore, in the thermodynamic limit, is determined entirely by this larger eigenvalue, lambda 1. And that's what I meant previously, that the statistical properties is determined solely by the larger eigenvalue, lambda 1. Okay, so now it's time to calculate this two eigenvalues, lambda 1 and lambda 2, from the transfer matrix. And remember, the matrix element of this 2 by 2 transfer matrix has this form, and to find the eigenvalue, the only thing we need to do is just to calculate the secular equation, where determinant of this 2 by 2 matrix is actually 0. And from that eigenvalue equation, we could simply derive the lambda 1 and lambda 2, which is some sort of exponential function of h and k, and where you have e to the k times coach h plus minus square root of this sinh square of k plus e to the minus 4k. So that's easy algebra to do. But we see clearly that since both h and k are positive variables, and all these terms, e to the k coach of h and sinh square of k and e to the minus 4k are all positive. As a result, immediately we know that lambda 1 is actually greater than lambda 2, because lambda 1 takes its plus sign and where lambda 2 minus sign. So the term with the plus sign should be clearly larger than the term with the minus sign. As a result, all these statistical properties are determined by this lambda 1. Okay, so we will use that in just a moment. So then we plug in this lambda 1 back to this free energy, which is the minus kBt times the log of this partition function. And here we divided this whole thing by this number of sites, which defined the bulk free energy density. Remember that, the little fn. And we could simply just reorganize, and we arrive the second line here, which is that the first term is just minus j is a constant, and second term is minus kBt times log of this coefficient plus square root of that thing. So let's see how the phase transition occurred if we have such a free energy density. So now we explicitly derive the free energy density analytically, and we should analyze this analytical properties of this free energy density and see if we could have a phase transition or not. So let's just look at the finite temperature property. So remember, in the very introductory lectures, I introduced how phase transition occur in principle. And the principle which leads to the phase transition is the non-analyticity of free energy density, right? So we need non-analytical properties of this bulk free energy density in order to have the phase transition, okay, as a function of this order parameters or external parameters or coupling constants. In this case, as a function of h and k. However, if you look at this little f here, constant, of course, just constant. And the key function is a log function. And you know very well that all these h and k are positive values, and the square root is actually a positive value as well, because this is the sinh square, which is a positive value, and plus e to the minus 4k is also a positive value. Okay, so when you sum up this all positive value stuff, you get again positive value stuff. And there's no non-analytic behavior of the log function here, so the log cannot be minus infinity or divergence or anything as long as h and k are finite. So this bulk free energy density, little fn here, is perfectly analytic. So this is a perfect analytic function of h and k. So from our earlier statement, the principle of a phase transition tells us that there's no phase transition, because this little f is analytic function. There's no way that we can have phase transition at any finite temperature, which agrees with our earlier statement and finding more qualitatively argument. But here we explicitly calculate the partition function analytically in this simple case, and we derive the same conclusion that there is no phase transition at any given finite temperature for a one-dimensional Ising ring. So the only way that we can have a phase transition is at zero temperature, which will be our next topic. The only chance that we have a phase transition is when this lambda 1 could be a non-analytic function of h and k, which will be the case under certain circumstances. And number 2, the square root is actually 0. When the square root is 0 and the limit of h goes to 0, and we can have some non-analytic properties of the log, because log 0 is actually minus infinity, right? But when that happens, we need the degenerate eigenvalues, namely when lambda 1 is actually the same as lambda 2. Then we have 0 of the square root. But is that possible? So we'll see that in just a moment. So there's a theorem called Perron's theorem, which says that for n by n matrix, or finite size n by n matrix, A with all matrix elements positive, the eigenvalue of the largest magnitude is the following. Has this property: A, it is real and positive, and B, it is non-degenerate, and C, it is an analytic function of Aij. Okay, so that's called matrix theorem, called Perron's theorem, which says that for a finite size n by n matrix with all positive matrix elements, and the largest eigenvalue has the property of three properties. Number one, it is real and positive. Number two, it is non-degenerate. And number three, it is analytic function of Aij. So we should apply this theorem here, the one-dimensional Ising model. From the transfer matrix, we know that this transfer matrix satisfies Perron's theorem because all the the matrix elements are positive, and it's an n by m 2 by 2 matrix, and the eigenvalue, the largest eigenvalues, is real and positive, and it is a non-degenerate, and it is an analytical function of Aij. So, in other words, lambda 1 is actually positive, and lambda 1 is not equal to lambda 2, and number 3, lambda 1 is actually analytic. So it satisfies all the three properties in the Perron theorem. So the reason why lambda 1 cannot be equal to lambda 2 is that the square root cannot vanish at all, right? Even when k is 0. See that when k goes to 0, h goes 0, it is non-zero. But when k goes to, say, infinity, and h goes to 0, you can have a 0 square root. But for any finite values of k and h, lambda 1 cannot be equal to lambda 2. In other words, the square root is always positive. Okay? So, in other words, this analytical properties follows the Perron theorem, and the Perron theorem actually fits pretty well to the transfer matrix properties of this one-dimensional Ising model. So, in other words, it is not possible to have any phase transition at finite temperature when both h and k are finite. So in other words, no phase transition possible for any given finite temperature, and h and k both are finite and positive. So that's the first conclusion, which is the most obvious conclusion that we arrive already, but we show more rigorously and mathematically how this conclusion arises, and we obtain such an analytical form of the eigenvalue and also the free energy density of the bulk, and it is a pure analytical function of h and k. As a result, there is no chance that we have a phase transition at any finite temperature. But there is a phase transition at 0 temperature, which is our next job in the next lecture. So in the next lecture, we will consider exactly this situation where k goes to infinity and h goes to 0 limit. Okay? So this is the limit of t goes 0, because remember, k is given by beta times j, and beta is 1 over kbt. So when t goes 0, beta goes to infinity, while this j is the Ising coupling, is always the finite positive value. So in the t goes 0 limit, the k goes to infinity. And when k goes to infinity and h goes 0, you get the chance to suppress the square root. The square root term becomes 0, and you have a chance of the non-analytical free energy density here, because log can be actually singular. So that's about everything we can do today, and I'll see you next time. And to finish this phase transition of a one-dimensional Ising model by explicitly calculating this partition function analytically. Okay, so I'll see you next time.